Hello, everybody. Good evening. And thank you for joining us for the inaugural Kuo-Nan Liou Memorial Lecture, established in memory of Professor Kuo-Nan Liou at UCLA. He was a distinguished professor of atmospheric sciences and the founding director of the Joint Institute for Regional Earth Systems Science and Engineering. My name is Miguel Garcia Garibay. I'm the Dean of the Division of Physical Sciences and someone who really benefits from the advice and interactions that I had with Professor Liou. That's something that I feel very fondly about. Now, in my role as Dean of the Division of Physical Sciences, I have the pleasure of interacting with a really amazing community of scientists, scholars, and students. And as many of you know, in addition to the Department of Atmospheric and Oceanic Sciences, that was the home of Professor Liou, we have other departments that are doing really incredible work in terms of research and education. And I just have to name them because, I mean, they're so good. I need to recognize them. We have the Department of Chemistry and Biochemistry, the Department of Earth, Planetary, and Space Sciences, Mathematics, Statistics, and Physics and Astronomy. We're also the home of the Institute of the Environment and Sustainability that actually is a shared home between some of the faculty in atmospheric and oceanic sciences. Unlike atmospheric and oceanic sciences, there's a lot of interest in aspects of sustainability, environmental sciences, and things of that sort. One of the nice things to brag about the Division of Physical Sciences is that out of 8 Nobel Prize winners among the faculty at UCLA, 7 have been faculty members in physical sciences. And of course, as many of you know, the most recent one is Professor Andrea Guest from the Department of Physics and Astronomy, who won the Nobel Prize in 2020. And she was only the 3rd woman to ever win the Nobel Prize in Physics. So, the atmospheric and oceanic sciences is one of the departments that really brings together many of the characteristics that make UCLA a really amazing institution. It's a small department, but it's an extremely cohesive department. I think the best way that I like to think about atmospheric and oceanic sciences is a planet that looks a department that looks at our planet in a very holistic way, from a system approach. Everything that has to do with our planet is looked at holistically in this department. And so, you know, our students and faculty really are doing amazing work that really makes the Division of Physical Sciences stronger. Atmospheric and Oceanic Sciences at UCLA is consistently ranked among the top departments in the country, which is a lot to say. And I have to say, of course, that the quality of the faculty, both scientifically and the human quality of the faculty, is amazing. And that's something, again, that we have a lot of things that to celebrate that we have learned from Professor Liou, that I think he was an incredible influence and impact in our community. So we're honoring Professor Kuo-Nan Liou today with this inaugural lecture. He was a great scientist, an outstanding leader. He had a profound impact not only at AOS and his field, but at UCLA. He was a chair of the department, and he remained active until very, very late. So he was always here with us, bringing his influence, his positive influence with all of us, until his untimely death in 2021. So we are very honored to be joined for this evening by Professor Liou's family. So we have his wife, Agnes, their children, Julia and Cliff, sitting here in the front, and Julia's daughter, Emma, who's learning about the incredible influence that her granddad had on the world. So thank you for being with us this evening and for giving UCLA an opportunity to recognize Kuo-Nan's long-lasting legacy at UCLA and beyond. So we're really grateful to have you here with us. Now, I would like to invite Julia to make remarks on behalf of the Liu family. Please, Julia.
Good evening, everyone, and thank you so much for being here tonight. We are just so greatly honored to be here, for all of you to just lift up my father's spirit of determination and always constant striving for improvement. And I just wanted to say that really he had such a legacy of vision and also just always striving for what's possible. I really wanted to give a special thanks particularly to Dean Garcia Garibay and also to Professors Qiang Fu and also to Qiang Fu as well as Mu-Ying Wang and also Qiang Fu and also Nancy Hom because you have all been like family to us over what's been decades. And so I just wanted to say that it's very fitting tonight that Professor Qiang Fu is going to be giving this first lecture, memorial lecture, in honor of my father, because it's a topic so relevant to our current times around climate change and even terms, I was reading your description this morning around atmospheric rivers, something that I just learned over the past few months. Really excited because my daughter's here, and we just started her first ever science fair project, 3rd grade. And when I asked her what she wanted to do, she said, let's do air pollution. So she has been cutting up paper plates, putting on Vaseline and putting them around our house in our backyard and close to the street just to see how much air pollution gets caught on those paper plates, those pollution catchers. So I'd like to think that, you know, the influence was because my father gave a birthday present to Emma when she was 4, his first published book. But it's probably because of school. So, but I just want to say, you know, I went to public health school here at UCLA, so it was really great for me to come back and see the public health school and just really just remembering just the spirit of UCLA and just the amazing school that it is. And so I just wanted to leave something that I've carried throughout my career of what my father stated at one point in time is to always carry others along the way to ensure success, and that dreams should have no boundaries or limits, to never limit yourself and have a determined mind with clear goals so that we can look forward and make progress together. So thank you again for being here, and it's such an honor, again, to be here collectively with all of you. Thank you.
Thank you, Julia. I have a confession to make. I also got a book from Professor Liu that I've studied a few times. It's about ice, and I'm getting through it. So now it is my pleasure to introduce Professor of Atmospheric and Oceanic Sciences, Pablo Saide, who will introduce our distinguished speaker. Pablo.
Hi, everyone. Thank you for being here. So I'm introducing Professor Qiang Fu. He's a full professor of atmospheric sciences in the University of Washington. He got his bachelor and master's in Beijing University, and after that he came to the U.S. and he got his PhD in the University of Utah together with Professor Liao. He's very renowned. He will be talking about climate. He's well recognized for his work in atmospheric radiation and remote sensing. He has a very, very long list of papers, but he also has a long list of awards. Within there included, he got the AMS Jules Charney Medal in 2020, and he's a fellow of multiple associations, including the Association for the Advancement of Science, the American Geophysical Union, and the American Meteorological Society. I was talking to him earlier, and he shared some memories that he had with Professor Liou. He mentioned that he went with him to multiple conferences or trips abroad, and he was quite surprised that people recognize Professor Liou, and a lot of them will reach out to him because of the books that he wrote, especially his Intro to Atmospheric Radiation, that he wrote the first version in 1980, before I was even born. And he was he told me that people will reach out to him and tell him how much influence he made to them just because of writing that book, right? So it's not only the people that he advised directly, but everyone that was able to learn through his work. He also mentioned that people will tell him, "Oh, you wrote this book so early, and you look so young." Let's give a good clap to Professor Qiang.
Yeah, thank you very much, Professor Pablo Saite, for the introduction. I would also like to take this opportunity to thank Senior Dean, Professor Miguel Garcia Garibay, for establishing the Kuo-Nan Liou Memorial Lectureship, and thank Professor Liu's wife Agnes, and daughter Julia, son Cliff, and the granddaughter Aima for the supporting of this lectureship. And also thanks for you guys coming all the way from San Francisco to attend this event. I would also like to thank the Vice Chancellor, Professor Roger Wakimoto, and your wife, Gina, for attending this event. It's my great honor to be the first speaker of this lectureship. Thank Professor Yu Gu, Professor Rong Fu, and Professor Suzanne Parson for invitation and also making the arrangements. Today I had a wonderful visit to the JFRC, the Joint Institute of Regional Earth Science, Earth System Science and Engineering, which was established by Professor Liou in 2006. And guided by current director, Professor Rong Fu. I also had a wonderful meeting with Professor Jim McWilliams, Professor Yongkang Xue, Professor Gabrielino, and Professor Bob, Babo, Saite, yeah, my name, Pablo Saite, yeah. And postdoc and graduate students in this wonderful, outstanding department. And thanks for the hospitality, and thank you all for coming to this event. So my talk today is response of terrestrial aridity to global warming. So I met Dr. Liou in 1986 when Dr. Liou gave a short course on atmospheric radiation at Peking University. So here's a photo we taking at that time, at the Winmin Lake, Peking University. And then I joined Dr. Liu's group in 1987 as a graduate student, then as a postdoc. So have been working with Professor Dr. Liou for 7 years before I taking a faculty job in Dalhousie University, Canada. Okay. So Dr. Liou, was my mentor, my colleague, my dear friend, and an inspiration. As many of us know, Dr. Liou is a giant in the fields of the atmospheric radiation, remote sensing, and cloud aerosol climate interactions. But less is known about Dr. Liu's vision and leadership, in the field of the land-atmosphere interactions. So Dr. Liou led the, initiate the, very influential, Hehe International field experiments in the 1980s. And then he also, lead the, Inner Mongolia grassland atmospheric surface study, so-called IMGRASS. So this is a photo taken at that time. Here is Professor, Liao, and here is me, and many people you may know, like Professor Bushinger, and So, the data actually at that time collected has already started to show the expansion of the arid and the semi-arid regions. So this talk would, devoted to Dr. Liao. So over the arid region, the air is always thirsty for water, but the precipitation does not provide enough water to ever quench this thirst. A more technical definition of the arid region is a place where the potential evapotranspiration is higher than much higher than the precipitation. Okay. So the potential evapotranspiration, so-called PET, is defined as a maximum amount of water capable of being lost from the surface for given atmospheric condition with well-supplied surface water. So this concept you can think about, you put a pan of water over deserts for given environment condition, how fast this water can evaporate. So this tells you how thirsty the atmosphere is. So this is so-called the potential evaporation, which is not actual evaporation. Okay. So this basically is the evaporative demand of the atmosphere. So this quantity can be calculated from the Palmer-Montes algorithm, which is derived based on the standard Bach formula for the latent heat and the sensible heat fluxes, along with surface energy budgets, by assuming the surface is saturated with water. Okay. So in this equation, the Rn is a radiation flux at the surface, G is a heat flux go to the deep layer, and the Ta is a near surface air temperature, RH is a relative humidity, and the U is a near surface wind, okay? And the E star is the saturated water vapor pressure, okay? Delta is a dE star dt, okay? So from this equation, the PET basically, as a measure of how thirsty the atmosphere is a function of temperature Ta and the relative humidity, RH, wind, U, and the surface available energy, which is Rn minus G, okay. So the United Nations Environmental Program defined the aridity index. I use AI, so this is not artificial intelligence, is aridity index as a ratio of the annual precipitation divided by potential evapotranspiration. Okay. So give me an example, at least, for example, Tucson, United States, okay, the annual precipitation is 12 inches. But the potential evapotranspiration, so that means if you put a pan of water there for a year, so it could, evaporate, 100 inches. So this tells you, based on this, the aridity index would be 0.12. Okay. So based on this definition, the climate is drier when the index is smaller. Okay. So the United Nations Environment Program, defines the drylands, as a region with a aridity index smaller than 0.65, okay, which further divided into like hyperarid, which basically deserts, okay. When the aridity index smaller than 0.05, arid for the index between 0.05 and 0.2, and the semi-arid, the index between 0.2 and 0.5, and the dry subhumid is 0.5 to 0.65. So overall, together is so-called the dryland. Okay. So here shows the spatial distribution of the dryland, including the hyperarid, arid, and the semi-arid, and the dry subhumid. Okay. So the dryland, comprises, more than 40% of the terrestrial land. And more than 1/3 of the population live, on, drylands. So in this talk, the question I try to answer is, how does the terrestrial aridity in terms of the aridity index, in response to, anthropogenic climate, change, and why? And how does this response affect the, area extent of global dryland? And this, I think, it's an important question, especially really before our research about 10 years ago. Really, no one, really look at this important issue. Okay, here is a review, a view of the dryland, with a village in the background, in the Sahara, southern Niger. So in my talk, I will, first, present the response of the terrestrial aridity to, greenhouse gas increases, and discuss warmer is more arid, mechanism. Then I will, show the aerosol effects on the terrestrial, aridity. Then, followed by, present the global dryland expansion in the response to climate change. So the data we use is, observation data we use is, from 1948 to 2010. Okay, the temperature and the precipitation from, Climate Prediction Center and the University of Delaware, and the radiation energy, at the surface, radiation humidity, and the wind from, global land data simulation system and the 20th century analysis. So each variable, we obtain the data from two different, data sets for the comparison purpose. So the model data we use is from 1948 to end of this century. Okay, we use 27 CMAP GSM simulation with historic forcing, from 1948 to 2005, and the future scenario RCP, 8.5 and 4.5 for, from 2006 to end of, this century. We also use 25, CMAP5, GSM, transient CO2 simulation. So that's basically increase CO2, every year by 1%, until it's double. So it takes, 70 years. Yeah, so this simulation say, how the aridity respond to CO2 change. Yeah, please feel free to interrupt me if you have question. So what I show here is, based on the model, projected changes at the end of this century, relative to 1961 to 1990 and the scenario. So this basically, we saw in the future change, we also have to assume some, CO2, change scenario. Okay, for this specific scenario, shows the surface, air temperature changes, the, PET, so that's really the measure of how thirsty, how the evaporative demand of the atmosphere, changes, and the precipitation and the aridity index. So as we expect, the temperature increase at the end of this century everywhere, and so does the, evaporative demand of the atmosphere. And for the precipitation, overall, you can say the precipitation actually increases in the, most of places, except in the subtropical regions. And, but on the other hand, if we consider, both, change of demand and the supply together, actually through the aridity index, the terrestrial climate become drier, in most of places, okay? Especially, in the region, like Mediterranean, and the south, west of the North America, Mexico, like for example, and the Amazon, and the southern, Africa, and part of the Australia, yeah. So that's because of the demand, increase, and the supply decrease force the system in the same direction, because the, terrestrial climate, particularly dry. So here is the similar figure in the upper panel shows the changes of the aridity index at the end of this century, okay? And the lower panel shows the soil moisture changes, at the end of this century, okay? You can see the pattern actually are very similar, so indicate that the two are closely coupled together, okay? And the changes in aridity index actually have important implication, to the, soil moisture changes, and also like, something more relevant here, like the wildfires, yeah. What I show here is the temporal dependence of the annual mean precipitation in the P, average over length as a function time, 1%, CO2 increase until double. How this changes, we say, it's increases. Okay, the solid line represents the, multimodal ensemble mean results, and the shading, shows the spread, from the model, simulations. Okay. So you can say, actually, the precipitation increase, overall over length, but the PET, so that's the demand, the evaporative demand of atmosphere increase much faster. Because this increase much faster makes the aridity index decrease, indicate, a drier terrestrial climate. Okay. So the global climate model predicts an overall drier terrestrial climate. If we use this as index, which consider both supply and demand in response to global warming. So the one question is this something what we expect based on some simple physics arguments? Okay, that's what I would like to discuss next. So the relative changes of aridity index average over length can be written down as a relative change of the supply, that's the precipitation, minus relative change of the demand, that's potential evaporative transportation. Okay, the difference of the two really look at which win. Okay, if this change increase faster would become drier. If this increase faster would become wetter. We know actually in the warming world actually the mean precipitation actually increase. Yeah. So in the lower in the figure I show here is annual precipitation changes, percentage changes. Oh, okay. Okay, I saw the my subtitle. Okay. So what I show here is the annual mean precipitation percentage changes scaled by SST increase, average over land, over ocean, and the globe. On the left, on the right, I show the actual evaporation changes, average, percentage change scaled by SAT change, average over land, over ocean, and the globe. So we can say the percentage change of precipitation, are similar, over land and over ocean, which is about, 1.9% per degree of SAT increase, which is about same as, actual evaporation increase over ocean. So this makes sense because, we know actually what's control, the precipitation relative increase globally is controlled by the, change in the actual evaporation over ocean. Okay. So if that's the case, so we can sort of change the comparison between the relative change of precipitation over land to the potential evaporation over land by replace this by actual evaporation change over ocean. Okay. But over ocean, actually, because over ocean is over water, so the actual evaporation is equal to potential evaporation. Okay, so in this case, the evaporation over ocean basically is a potential evaporation. Okay, so which can also be, estimated using the Palmer-Montes algorithm. So in this case, we can, estimate the two terms in the same framework, in the same framework. So this is when we apply the Palmer-Montes, Palmer-Montes algorithm over ocean, that's what we get. The actual evaporation, the percentage change of evaporation, the percentage change of the evaporation over ocean scaled by SAT change, and the near surface air temperature change minus skin temperature change scaled by SAT change. Okay, the upper row is from the Palmer-Montes. Okay, the number in the parentheses shows the spread from different model. Okay, the lower row shows the results directly derived from global climate model. So you can say these two actually agree very well. Like for example, the percentage change of actual evaporation from Palmer-Montes is 1.9% per degree temperature SAT increase, and from model is like actual from model is 1.7. Okay. So we can sort of replace this by, relative change, presentation by the relative change over ocean. Okay, so then we can sort of, really compare this in the same framework of Palmer-Montes algorithm. So now, because, both, PET over land and the E over ocean are function of the surface air temperature. Remember I showed the equation, and the relative humidity, and the wind speed, and available energy, in this framework. So this, we can gain insight about these two comparisons by comparing the, change of each variable, over ocean with that over land. Like, for example, temperature change over ocean compared to that, over land. Okay, first come to the temperature change. Okay, so what I show here is a temperature, increase, scaled by ocean temperature increase. By definition, over ocean would be 1, but then over land we found, from different model actually with an average about, 50% more than over ocean. Okay, so this is actually well established, phenomena both, from, Suki Manabe's pioneer work and based on observation. Okay, so but we know actually the evaporation over ocean and the potential evaporation over land increase with temperature. Because the ocean temperature increase, the evaporation over ocean increase. But the potential evaporation actually over land increase more because of temperature over land increase more than temperature increase over ocean. Okay, so that's one of the components. So then we compare the relative humidity change, from the model, over ocean, and also scale by SAT, and over land, okay, scale by SAT. So we can see actually the relative humidity over ocean actually from all models show the relative humidity actually increase, but over land, decrease. And we know the potential evaporation over ocean, that's actual evaporation over ocean, because of relative humidity increase, the evaporation would be decrease. But the potential evaporation because of relative humidity, decrease would be increased because the relative humidity decrease due to the, increase of that. So this also contributes to the difference between the potential, evaporation change and the actual evaporation change over ocean. So wind actually, does not change much and does not have much difference between the two. So it has small effects. Okay. Then available energy. Okay, available energy. So both actually, in terms of watts per square meter, reach a surface increases in both land and the ocean. But what increase over land is more than over ocean. So that means you can imagine, because we know the potential transportation over land would be increased with available energy, and the actual evaporation over ocean, that's basically potential evaporation over ocean, also increase with available energy. But this increase more. So you would say, this also, contribute to the difference between ocean and the land. Okay. So I think it's very interesting to really look at the radiation, yeah. So for the radiation, actually, if we look at the radiation, flux density, actually, both increases over land and over ocean, but when you look at the over ocean, even increase slightly more. But because over ocean, actually, this also well established from, from the previous work, both based on, modeling and observation. Over ocean, the energy increase in terms of radiation, actually part of it go to deep ocean. Okay, so that makes the G, is positive. So Rn minus G, okay, become less than, Rn minus G over land, because G over land basically does not change much. Yeah. So when we put the whole thing together, okay, here before I say that, I think it's also interesting to look at the radiation, solar part and the long wave part, the changes over land, over ocean. Okay, so like over land, the solar radiation at the surface actually increase more over land, but the increase less, over land. Okay, okay, sorry, I sort of pushed the wrong button. Yeah. So this basically the interpretation of this actually is over land because of less clouds, So that's, have less albedo effects, make the solar radiation increase, but then also less greenhouse effects, make the downwave, long-wave radiation, increase less than ocean. So this is also consistent with, dry terrestrial, climate. So put the story together, okay, there are three factors contribute to the difference between ocean evaporation. So that's determine the precipitation over land compared to, demand, that's potential evapotranspiration. One is temperature, okay? So if you think about temperature increase, the E over land, over ocean would be increased, but the PET over land would be increased more, okay? When consider relative humidity effects, the E over ocean would be decreased, but the relative humidity decrease, over land push this even higher. Okay, for available energy, both increases, but the potential energy, the PET increase more because the available energy increase more. Okay, so this can be explained the difference between the two. So based on our scale analysis, actually we found, on terrestrial mean aridity index actually, decreased by 3.4% per Kelvin of the SAT increase. Okay. So this is exactly what we derive from global climate model. Okay, the precipitation actually increase over land average by about 1.9% per degree temperature increase, and the PET actually increased by 5.3% per K. Okay, so on average this is about 3.4% decrease. Yeah. So we would argue, that the relative, increase over ocean, the actual evaporation over ocean, which determine the precipitation increase over land, is lower than, relative change in the demand, in the evaporative demand. That's PET over land, which lead to the overall dry terrestrial climate in the warming world. So that's an argument here. Okay, next I would like to switch my gear to the impact of the aerosol effects on the terrestrial climates. Okay, so what I show here is changes in the surface air temperature, precipitation, the PET, and the aridity index. Okay, the black line shows scenario 8.5, and the blue line, the red line shows scenario 4.5. And the blue line shows the scenario, same as 8.5, but we fix the aerosol at the present climate. So that means, so in the future scenario, we sort of, project the aerosol would be decreased because of the pollution, control. Okay, but now if we don't consider this decrease in our simulation, fix the aerosol concentration at the current, climate level. So that's the blue line. Okay, so compared to the consider all changes actually without consider aerosol in the future, decrease. Of course, the temperature increase would be less, and so does mean precipitation and the potential evapotranspiration. And what's interesting is aridity index actually does not change because of aerosol effects. Okay, so we would argue the unsubjected aerosol have small impact, at least on the terrestrial mean aridity index. And the terrestrial mean aridity index change would be largely driven by increase of the greenhouse gas. So to understand this, here I show the attribution of the terrestrial mean aridity changes to different meteorological variables. Okay, for different situation. Okay, we consider one. We consider if we have 1 degree of the global mean temperature warming. Okay, so now we have minus 2.7% of the aridity index decrease. So that's mean dry climate. This number is the magnitude smaller than the number I gave because here is scaled by global mean temperature increase. Before I scale by SAT, temperature. Global mean temperature increase is larger than SAT, so make this number smaller. Okay. So when we do the attribution between different variables, we can say this is largely determined by the temperature changes. By temperature changes, okay, temperature increase makes the atmosphere more thirst. The precipitation increase largely cancelled by the component related to the relative humidity and available energy. Okay. Then consider another situation, because of the aerosol, we have cooling. Okay, we have cooling, because of aerosol. So in this case, actually, what we get is the net change of aridity index actually become almost zero. And so the precipitation decrease contribute to the aridity index change a lot. This is also well established because we know the hydrological sensitivity is, respond to, non-absorbing aerosol is much higher than in response to, greenhouse gas increase. And this is largely, compensated by the temperature effects and the available energy effects. So when we combine these two together, so that means, 1 degree warming, plus 1 degree cooling, so global mean temperature would be zero, right? So now the combined together, we still get about, like minus 2.8%, still drier. So the aridity index, like I showed, does not, affect by aerosol. If we combine this together or not, this is same as this. But the aerosol does affect attribution. So here, if we don't have aerosol, the world become drier is because of temperature increase. But in this case, the terrestrial climate become dry is because of we have less precipitation. So attribution are different. So this have a very important implication for geoengineering. Okay, suppose in the future, global warming, we put the aerosol in, one way or another, we sort of, compensate the warming effects. But this sort of geoengineering may not, really be lead to the, global mean temperature change is zero, but does not really solve the problem of aridity change, which is always become, drier, will always become drier. Okay. Another implication is, detection attribution. So in this world, this is mainly due to temperature. So that makes the detection attribution much easier because the annual variability or, natural variability associated with temperature change is much, compared to, precipitation is much, smaller. So make this detection much easier than this. Yeah. So this is what I say, the geoengineering through aerosol may not be able to address aridity changes caused by greenhouse gases. Just, changes the attribution from, from more demand to, less supply. Okay. And the effects of anisotropic aerosol makes the detection attribution of present-day climate change in terms of aridity, difficult because of much larger, natural variability in precipitation than the temperature. Okay. So the United Nations Environment Program, defines the global dryland in terms of the aridity index. As I showed, the aridity index actually changes in response to, anthropogenetic forcing. So we would expect the dryland area would also, respond to, anthropogenetic forcing. So what I show here is temporary, dependence of the global dryland area in A, okay, and each components, like dry subhumid, semi-arid, arid, and hyper-arid, from 1950 to end of this century. Okay, so the black line shows the scenario 8.5, and the blue line shows scenario 4.5, and I also show the shading for the spread of the 8.5 GSM simulation. The red shows the results from observation. Okay. So first look at what the results from the model. Okay, the model basically show at the end of this century, the area of dry land actually is become 6 million square kilometer larger than current area. So which is about 10% larger. Okay, this is contributed by different components, especially semi-arid and arid. Okay. So in another hand, we say the results derived based on observation actually show dryland expansion is much faster. Okay, so what caused this? Okay, to understand this, so we compare the model results with the observation for the temperature, annual precipitation, annual potential evapotranspiration, and the dryland area, put here. But here, the dryland area we derive from different observational data set, combination of 4 data sets, all show same results. The increase of the dryland area since 1980, increase. But the model, does not show that. Okay. But when we see the comparison of the temperature, actually the model agree with observation 2 data sets very well. And compared to PET, that's combination of two, actually data set have different four combination. Also agree, very well, model with observation. But the precipitation is not. Actually, precipitation, we say the precipitation from the simulation actually increased since 1980s, but the observation decreased. So what's caused this? So here we compare the model, simulation with observation, not only from coupled simulation, but also we use the AMAP simulation. AMAP is a global climate model simulation, actually by prescribe the ACT using observation. So if we use the prescribed observation driving the model, actually the model simulation agree with with observation reasonably well. Not only in temporal dependence, but also in trends. But the coupled model on some mean does not catch this. Yeah, does not catch this. Yeah. So this could be largely due to internal variability. Internal variability could be the reason. For the PET, actually the model and the observation agree very well. So we would argue the natural variability in precipitation, related to the PDO, and so on could be, respond to the difference in the dryline expansion between model simulation and the observation. Yeah. So here I show the changes of the dryline, coverage at the end of this century. Okay. So the yellow shows the humid to subhumid, and the orange shows subhumid to semi-arid, and the red shows semi-arid to arid. The black shows arid to to deserts. Okay, I mean there's a few places in California actually become overall all become drier. Okay, in terms of index, but particularly this also change from arid to deserts, and some places change from semi-arid to arid, and of course also many places in Mexico also have big changes. I will use the last few minutes to talk about implication of the Aridity index to droughts. So droughts, I use the Palmer drought severity index, so-called the PDSI, okay, which is based on the supply and demand model for soil moisture. Okay, the NOAA actually publish the PDSI map weekly. Okay, so this index is commonly used to monitor drought. Okay, so in the current climate, here I show a schematic figure of the probability density function of the PDSI. Okay, for example, in current climate. So we often define the droughts as events whenever the index is smaller than some threshold. Okay, threshold. Okay. So in the future climate, actually the mean value of the index can be shift left or right. Okay, if shift to the left, I mean, for example, for this case, this is the current climate. In the future, if the mean value shift to the left, using the threshold, you have the frequency for the droughts would be more common. Okay, and the PDF, the shape can also change even for giving the mean value. Like for example, for giving mean value, the present climate, if it's become wider, okay, the shape become wider, okay. So that's, could also, given the threshold, could also make the drought frequency higher. Of course, in the future climate, the PDSI mean value could be either go this way or this way. The shape could become even wider or narrower. Okay. So let's take a look what's happening in the future. Okay. So here I define the droughts as the PDSI less than 10 percentile of the PDF, probability density function, and the current climates. Okay. So what I show here is that at the end of this century, the frequency of the drought changes. This shows due to mean value change, the mean of the PDSI. Okay, you say some places, become more, some become less. Okay, so this is, the frequency change due to the, shape of the PDF function changes. Yeah. So this is consider all, factors, both mean and the shape. So you can say, at the end of this century, everywhere in the world, the drought frequency become larger or more frequent in the future. The only place is Alaska. Otherwise, the drought frequency would become higher. But the dots mean is statistically significant. Like 80% of the model agree on time. So by looking at this figure, you may remember this is basically the place very much corresponding to aridity index, where the index becomes smaller. Okay, so this pattern basically is determined by the aridity index changes. Let's take a look. So like if we plot the PDSI mean changes as a function of aridity index changes, actually we can, the changes of this is for each point of the world grid box from more than 20, 30 models altogether. So the changes of aridity index can explain actually about 60% of variance of the PDSI mean changes. And one exciting thing is about the shape change. I think it's very also interesting. So you can notice actually that wherever the drought frequency increase due to the shape change often happen due to the mean precipitation changes, mean precipitation increases in the subtropical region like Mediterranean, Amazon, and the southwest of the North America, all become less. That's the mean precipitation decreases. So now let's take a look at how if I use the standard deviation of the PDF function, as a measure of the shape of the PDF. I plot as the mean changes, precipitation. So we can say, the shape change can be well represented by the P changes. So this is very exciting. I think it's a very, very important result because in this case, we sort of relate the extreme, events, the change in the future. That's something we usually have less confidence to the changes of the mean, variable, like aridity index, like the mean precipitation. Okay, so, I think this physics behind this is where we understand. I think this is something we are still working on, try to understand. But this, if that's the case, I think this is very important because, if we have solid physical basis for this too, so that means in the future, the higher drought possibility happen in the future, we can well explain by the mean changes. So and we have confidence on the mean changes. So then we have confidence on the extreme event changes in the future. So I would like quickly give some results. The climate over land will become drier in the warming world in terms of aridity index. And the relative increase in actual evaporation over ocean is lower than the relative increase in the potential evapotranspiration over land, leading to a drier terrestrial climate. And the unsubjective errors have small effect on the terrestrial mean aridity, but the change is attribution. And by the end of this century, the world dry land can be about 10% larger than the current climate. And the severe drought frequency increase everywhere at the end of this century, but which can be largely explained by the changes in aridity index and the mean precipitation. So I would end actually with these slides. Roger may still remember this is Dr. Liao, gave a speech during the MS, annual meeting, 2018, when Dr. Liao received the Rossby Medal. That's the highest, award, in our society. And this figure actually is a time when we visited, Dr. Liao's family in 2019. Yeah, and this is actually a picture actually in 2014. Yeah, 2014, I think that the year when I get the AGO fellow, I think, yeah. Yeah, here's a paper we have on this subject. But anyway, so I stop here and welcome for, yeah. Thanks for coming.
Given your aerosol analysis, that means that the most commonly proposed
Yes. So I will, yeah. Yes, yes, I would agree. I think in terms of aridity index, actually geoengineering cannot do much. Although it can, help to reduce the warming, but does not help at all in terms of aridity index. And even worse, it's actually, reduce the precipitation. Yeah.
More harm is done by aridity than warmth?
That's a good question. That's depend on your the environmental problem you look at. And for the wildfire, I think this would be more important. Aridity index would be more important because that directly controls the soil moisture, and the soil moisture would be very relevant to the wildfire. I mean, but if you look at precipitation or river runoff, it would be different story. So one of the arguments actually in our series paper, we say, to address the complicated, environmental problem, we have to use different index. Sometimes use precipitation, sometimes use runoff, that's precipitation minus E. Sometimes use the aridity index. Yeah, sometimes using the vegetation coverage. That's a more complicated story. Yeah, thanks.
So the calculation of PET seems to a novice like me to involve an assumption about some sort of equilibrium between the air and the surface.
Yeah.
How much does that depend on the actual soil composition? Because obviously, in addition to what Jim just said, one of the sort of geoengineering things that has been done in urban areas is to change the surface properties to retain moisture. So what can you tell us about differences in mineral composition and soil composition as a kinetic effect to damp down on the PET?
Yeah, so I would say the response of the process, the PET would be very quick. Spend no time. Over land, it's different from over ocean. Over land, response would be just quick. Yeah, so instantaneously, I would argue. Yeah, so like for example, of course, the process, you put aerosol in the atmosphere, reduce the temperature, whatever, that takes some time, right? Especially, when you consider the ocean, ocean is really something controlled. On the thumb road, what's happening over land is controlled by over ocean. So even you put the aerosol in the atmosphere, it really changes the ocean temperature first. It changes the land temperature, but eventually what determines the actual temperature change over land very much, related to the ocean. But then, given the, change, the surface, PET would respond immediately. Yeah.
Oh, yeah. Well, thank you so much for wonderful talk. Actually, just yesterday I was reading a paper related to your work. And one question in this paper was, I think the last author was Justin Sheffer.
Yeah.
And is how do we define aridity? Because all of us were meteorologists, we come from physics background.
Yeah.
We use the soil moisture as an indicator of aridity. But for global warming, as you increase CO2, and the plant actually doesn't transpire as much when they simulate the same amount of carbon. As a result, their water use efficiency increase.
Yeah.
So this article actually point out this apparent inconsistency why global climate model project decreased soil moisture as you present, but they also project somewhat increase of the carbon simulation because now plants does not need so much water to grow. So the question is, how do we define dry land, right? Because we can define by soil moisture. This is not a question just for your talk. I was thinking, how should we define dry land? We define dry land by soil moisture, but in the elevated CO2 environment, the plants also does not need as much water.
Yeah.
soil moisture.
So that
So it's a more
that's
broad question whether
That's
you
a
have
very
given
good
thought.
question. I think, I mean, like I say at the end of my talk, we really, for different environmental issues, we have to use different, index. I mean, like for example, Aridity index I use here is very simple, directly related to the meteorological variable, related to thermodynamics. I mean, this basically, when you can think about it's sort of more or less, very good measure of soil moisture. And why we don't want to use soil moisture? Because I don't have, equation for that. Soil moisture, I mean, could be very, very complicated what determines the soil moisture, right? But, okay. So now, I mean, so I would say, what we define here would be have direct, application to understand the soil moisture changes. I mean, instead of using the complicated model, I can just, based on simple thermodynamics, I know this would happen, right? This have very important implication, like I say, for the wildfire, okay? But then we talk about another thing, you say how affect the vegetation, not totally different story. Would be very complicated because like you say, when the CO2 increase or the aridity increase, but the water, the vegetation can make use of the water more efficiently because the stomatal, opening become smaller, becomes smaller. So it's very, and also the CO2 is a fertilizer. So you can, even the aridity index actually become drier in terrestrial climates. Even the vegetation would be even become more green. So it really depends on your applications. But here, I really don't want to touch the vegetation because that's very, very complicated. So now I just want to, based on thermodynamics, what we can understand based on simple, physics. No matter, even eventually or another thing about dryland, remember the dryland is the area, the vegetation coverage may not as much as in the humid region. Okay, so the role of vegetation, I would argue, over dryland, like every region, semi-arid region would be less important than over the humid region. So the key is, really depend on your problem, your look at. Like for example, some people like to look at the aridity if you use the precipitation. So we know actually in the warming world, the mean precipitation actually increase. We know that. So you say the world would become, whiter, right? But I would argue, although your supply become more, but the, demand become more. So I would argue become drier. So really depend on your problem you are look at. Like people use the runoff, like R, precipitation minus evaporation. So that's another application for the runoff, the water. Yeah.
Hi, that was a really wonderful talk. I love the way you framed it. It set up the problem very nicely, and I TA a climate change class a lot, and I love the way you set it up. We talk so much about like the wet get wetter, the dry get drier, and we just present this very digestible story to a lot of the undergraduates. I'm curious though, one big thing in general in that class that we talk about, and something I wonder about, coming from like an oceanic background, I don't have as much breadth of knowledge, but as we begin to resolve clouds better in all of these models, how much do you anticipate these results to change? And do you think the main story will be similar, but I'm curious, if we did have better cloud resolving in our models, how much the story will vary from what we have right now?
That's a very good question and also a very challenging question to answer. It's a still great challenge to simulate cloud correct in the global cloud resolving model. And but I think one of the we see the hope like you mentioned the global cloud resolving model actually more and more used to understand the cloud respond to climate changes. So that means we don't really need to in such model we don't need to parameterize the clouds. And I would say so that what I argue here, the dry in the warming world is the terrestrial climate overall become drier
I mean, I sort of argue based on some sort of large-scale, thermodynamics. So I would say not much affected by, by the clouds, because we know, based on the modeling theory and the observation, we know in the warming world, land increase temperature would be more than ocean. That's well established. And we also know the radiative humidity actually slightly increased over ocean, but decreased over land. So this is also well established. And also over land, over ocean, part of energy increase, at the surface go into deep ocean. So based on this, we argue, the evaporation over ocean have, relative change have to be slower than potential evaporation over land. But your problem is very important for the extreme precipitation changes. So we know in the warming world, actually, we have more severe, storms like the atmospheric river. What's happened since last December, we have dozens of the atmospheric river hit the place. I mean, this would become more common in the future because, like you say, in the warming world, actually the storm get more severe. But how much? How to quantify that? This is an extremely challenging problem. We really need to understand how to simulate the cloud correct, to understand this, So that's I say, whatever insight, physically based insight to understand the change in the extreme events would be very, very important. So that's why I'm excited about our recent study when we look at the droughts in the future, when we relate it to the mean state changes, because we have more confidence on the mean changes. Yeah. But your problem is, still it's a multi-million-dollar problem.